Hello everyone, welcome to the session 4 of the labs. So in this lab, I would recommend each and every one of you to go through the lecture slides for all the lecture slides discussed for design compiler, that means complete unit 3 and all the 3 labs. You should be very comfortable at the end of lab 3 before beginning lab 4. Lab 4, I'll discuss about some miscellaneous items about the different formats that you could write out and how you could read in those formats of design. And then I would discuss about some advanced concepts in synthesis. I would take up one more example of a design. I would clarify what virtual clocks are, what are the math delays. So since these are somewhat advanced topics, I would recommend that you be very comfortable with lab 3. You should understand everything that is discussed in lab 3 before going on to lab 4. So just clarifying one thing before starting is that I am using one alias called LT. LT is not a Unix command. So I have put this in my source file alias, and I use this. So LT is an alias for ls minus LRT. This is what I use for listing down the files in order of time modified. So yeah, you could choose to use a different sort of LT command or something like that, different sort of ls command. So please don't be confused. LT is not a Unix command, just an alias, right? So let's go to the. So this time I'm not using the design I have been using for the first 3 sessions. I'll be using some of different design. So I've copied the RTL again here, and I'll be working in work directly. So this is the design, and this is the hierarchy of the design. So the top level is called chip level. It has a 16x16 multiplier, 8x8 multiplier. It has a mux module. It has then a cascade module has a couple of 8-bit adders, a comparator, a counter. And it has a 16-bit adder. Again, there's a comparator at the top level. So this is not a real-world design. It is just a bunch of data path components assembled together to give to help us in understanding some of the concepts. So you could look at the RTL files. They are very simple comparatively. This is a bunch of RTL files used. So adder 16 is just so adder 16 is nothing but it just registers the input. I mean, it just adds the 8-bit registers. 16-bit registers. So A and B in are the two 16-bit inputs. So the carry out and sum is just in plus B in plus carry in. Carry in is also one of the inputs. So most of the modules are of this kind. There's adder 16, adder 8, multiplier 8x8, multiplier 16x16. Let's go to the work directory. So what I did, I've written out a bunch of DDCs and Verilog files. I've tried 2, 3, 4 different types of synthesis. So I've already synthesized them to save on time and to show you quickly what I want to be shown. So let's first discuss the difference between writing out DDC and writing out a Verilog file. So let me open DDC. Now the write command supports multiple formats. 2 of the most famous formats are DDC and Verilog. DDC is the synopsis internal binary format, and it is recommended to be used if you are using synopsis tools further down in the design flow. However, if you are using any third-party tool for backend, they will not be reading DDC, so you would need a Verilog file. But there is one major difference between DDC and Verilog file is that DDC contains the constraint concept, not simply the design information, but also the constraint. So what I'll do, I'll read in the DDC of one of the flavors of synthesis, as the name suggests. So I am reading in the DDC of no IO delays.ddc. This is the synthesis I have performed. So yeah, now see, I read in the DDC, but now what has happened is that it read in the DDC file, but it did not find the library. Why? Because I haven't set the link library in a target library. So what I would do is I would start again. I would remove the design. So this is to show you that you should first have all the variables set, and then you should read in the design. So I have set in the important variables. These are the important 4 commands. So I have set all of them. Now I again read this DDC, and now so when we read in DDC, you should always when you read it some design, some synthesized design, or even RTL, you should always make sure that your top level is set correctly. So it tells me here that this current design is tip level, and you could also verify that the current design is in fact indeed the top level design which is tip level. Now the next step, so when we read in the RTL, complete RTL using analyze command, we should do elaborate on the top level design. What does elaborate do? Elaborate converts the RTL into GTEC, but here it is not RTL, it is already a netlist, it is already in gate level form. So we would not use elaborate, but we will use a command called link. Link will just make sure that all the components in your design are mapped, and all the libraries that you have loaded, and all the components are in fact linked to one library or the other. So here it tells me that the memory has 12 designs, and this is the DDC that we have read, and this is the library, right? So this linking is okay. Earlier it complained that cannot specify a library because DDC contains a link to that library, and since the target library and link library were not set, so it gave it error. So now this is already synthesized design. Now let's look at, so it also has constraints because it's a DDC, it's not very long, right? When we write out DDC, the constraints are also written out. So it already has a clock, which is a clock of 2 nanoseconds created on the port CLK, and it does not have any input output delays, although it does have so I do a report port minus the report. So it does not have input output delays. What it has loads on the output, which is 10. It has so there is no input delay. The input delay table is empty. The output delay is also empty. It has transition. So it has a transition of 0.5 on inputs. So I have just defined the environment constraints, but no IO delays. Now I synthesized it without the IO delays with just the clock in place. So these are the constraints file I use. I set the operating condition, I set the input transition, I set the load, I created the clock, I set the clock uncertainty, transition, and I just did the compiler, the standard options. Now synthesis is done. I wrote out the DDC. I read in the DDC again. Now if you would have read the Verilog, then only the design would have been in the place. You would have to reapply the constraint. So what we could also do is we can write out the constraint by using something called write script. So if you see the help, the write script, so write script also supports different formats. So what we do, we say write script. So our most famous format is called SDC, synopsis design constraint, or there's also a TCL, which is the DC pickle format. So I'll use the DC pickle format. So and I write dot pickle. Let's see what it writes. Minus output. Let's open this dot pickle. So it wrote the units, operating condition, link library, pin load. Now see, the single command we issued, set load, on all outputs of the value of 10, it translates into so many set load commands on each of these ports, and it contains the clock information, input transition, and so on, right? So this is the constraint that DC wrote out for you. Now, so there are two choices: either I read in the, so I want to read a synthesized design, either I should have a DDC or I should have a verilog and a constraint, right? Or the original constraints in tickle format like this, something like this. So usually when I want to deliver the constraints to the backend for place and route, I would give the verilog plus this kind of a constraint. Now let's go back to design compiler. Now the design is already ready. I want to show you the report, the constraints report, right? So I've already written out that there is a, so with this particular DDC, let's first look at how to write out these reports. Right? Now let's look at some report timing examples. Now first let's look at what are the constraints that are violated. So report constraint minus all violated will give you that. The minus option. So this was the, these are the only violations in the design. All of them are hold. As I've discussed before, do not worry much about the hold violations, small hold violations in synthesis. They are expected, and it is expected that we should not solve them in synthesis. They are better solved after the place and route is done, after there is some clock tree in place. I will come to that later in unit 5. So there is no setup violation. All the but the fact is that there are no input and output delays, right? The only delay, the only constraint parts are the register to register part. So if I do a report timing by default will report the worst case violator for each path group. Now since there is only one clock, there is just one clock group, which is clock, which is the group, and it will tell me what is the worst path. Right, so I give this. Now it is telling me that this is the worst path. Start point is the register, and then the register. I will not discuss the report timing format again. Please refer to the math lab if you haven't understood it clearly. It tells the complete path, and then we see that there is no violation. It is null. Slack is null, and it is meeting by 0. That means it is barely met. Right. Now there is one thing called critical range. What it means is that the command is called set critical range. It has these many options. Now what happens is that DC will optimize, and we have seen that it uses multiple iterations to design the system, to do timing optimization, to do everything. Now, by default, when you do not do anything special, when you do not issue any special command, DC will try and fix from the worst paths that are violated. Now, if your design is so, and it will then do area recovery, so it will focus its energy on the worst violators, for which the slack is less than 0. Now for some reason, let's say you are doing some trial synthesis and you want, so now in this case you see that slack is actually 0, right? Now some people for some special cases may want that, no, I do not want a 0 slack, I want some margin, I want the slack to be positive, let's say 100 picosecond or 0.5 nanosecond or something like that. You can use set critical range to control that. This is again an advanced feature used for very specific cases. So what it does is that you could specify a case, specify the values to which critical range attribute is to be set, and you can tell what designs it should be set on. So the compile command will use this attribute of the software design as a default critical range for the path groups that do not have this set. By default, the value is 0. That means it will fix the 0. We can assign this critical range using this critical range command. It also can be used in group path, and we can assign a positive floating point value greater than 0.0, right? Greater than 0, and then so a critical range of 0 means only the most critical paths are optimized. If we specify a non-zero value, then the near critical paths within that amount will also be optimized if possible. So you could say that you could set the critical range to be 10 PS for example. So DC will try and optimize till 10 PS, all those paths that have slack between 0 and 10 PS. So this is a you could try it out. If time permits, then maybe in the next session we can try one example of this. But it's again a very special use case. If you won't encounter its usage very frequently. So now what happens to the input and output path? So we reported paths. So we saw that only there are only hold violations, there are no setup violations. But so how to report the path starting from input? The worst path. You could say something like this: report timing from all inputs. Now it tells us that it gives us the worst path again. Start point, input port, endpoint is a register which is clock by clock, but the path group is none. Why the path group is none? Because there is no input delay. Although the input delay is assumed to be 0, but DC does not know that what clock, it cannot choose any default clock. So because since basically whenever we specify input or output delay, we should also tell which clock is it referring to, and there is no input delay defined. DC assumes a value of 0. It cannot assume anything else, but it doesn't know what clock it is on. So it will just say that path is unconstrained because there is no target time to which this data should arrive. And please note that there are a lot of full adders in the design. It is going through a multiplier. So the path, two important things: path group will be none, and path will be unconstrained if you do not specify any input delay, right? Similarly to outputs, how to report timing to outputs? We say report timing -2 all outputs. Now we see again path is starting from register, is going to the endpoint output port, and path is again unconstrained. Now here DC doesn't even tell you that there is an output delay, because again the output delay forms the part of the data required time. So there are two sections, if you remember correctly: data arrival time and data required time. Output delay forms the part of the data required time, which is not here, not present here, because there is no required time, there is no constraint. Input delay forms the part of the data launch part, so it assumes a 0, right? So these are unconstrained. Now DC here is free to reclaim area. If it reclaims area, in that case the path will be very slow, right? So let's see what is the area. So okay, there is some area. Total cell area is 5205. Now is it good, is it bad not to have an input and output delay? Let's see. Now one more example of report timing. Now I want to report timing, report the worst case path from starting from a register and into a register. I want to report the worst case path among all register to register paths. In this case it's easy because input and output delays are not specified. I can just do report timing, and the worst case path that comes is in fact a register to register path. Why? Because there is no input, all the input paths are unconstrained, all the output paths are unconstrained. Report timing by default will report, you have to remember this, it will report worst path in each clock group, worst single path. If you want to, so if you want to report multiple paths, you can say n minus max paths, let's say 5. It will now give us 5 worst paths, right? All of them. So these are the 5 worst paths, right? Now I have a second version of this design where I have done this. I have specified an input delay of 1 on all inputs and an output delay of 1 on all inputs. Right? One more type of path could be there, starting from input, ending in input, output. We could report again, report timing minus from on inputs minus 2 on output. So these type of paths are completely combination paths. For example, it is going from a cell 0 to north south. We see that again input external delay is assumed to be 0, but the path would be unconstrained, right? So this is one more example. So we saw that input to register is unconstrained, register to register is fine, register to output is unconstrained, input to output is unconstrained. Right? Now I will remove this design and I will read in the DDC of the design with input delay, input and output delay. Right? So I will say remove design minus design. I do not want to remove the library, so I will not do all. Then I will read in the DDC. What are the DDC present? DDC with IODelays.DDC. Again, current design is correctly set. I'll just do a link. It's fine. Then now I want to do report time. Right? Now let's see the report constraint first. So it gives you a message that it is updating design, updating graphics, it is updating timing. So it has the design info, it has the constraints, it just needs to do a little process under its hood to calculate the timing and to give you all this class. Now this is the problem. Now there are set of violations. These are the endpoints. So we see that okay, there are some outputs on which there are violations. These might be input register path, register to register path. We do not know since only endpoint is listed. So now there are a lot of violations, right? And plus the whole violations compared to the one where we gave input and output. Now let's analyze where these violations lie. First, I want to check what are the violations from the inputs. So again, I will report timing from all inputs. Now this is a violation. This is the worst path from the input group. Now I see that okay, input delay is 1. DC did some optimization. Now if you remember the the earlier path where there was no input delay set, the input to register path was very long. The worst case path was about it was about 3 nanoseconds. Now here DC has done some optimization because there was some constraint, and since there is a violation, we know that DC has worked here, right? It has optimized. Now we do not see so many levels of logic. We could go and compare the timing of input to register path in this DDC and without the IO delay DDC. You would find that the paths are much more optimized here because there is a constraint. So DC can only optimize when there is a constraint. So okay, there is violation from input to register path. I know I have the frequency is very fast. It is like 500 megahertz. The input here is not registered. Input is going through so many levels of combination logic to the register. So with this, I know that the design is not good, right? It's not a real world design. The input, all the inputs should have been registered. There should be a flop right after the input. There should not be any combination logic. In that case, it would meet our requirement. It would meet the input external delay of 1 nanosecond. It can even meet 1.8 nanoseconds. So the design is very simple. What I want you to do is, as an assignment, try and correct the design so that the input to register paths are good for timing. How do you do that? You register all inputs. Similarly, I want to see the output path. Report, I will say report timing minus from all inputs minus to all outputs. Oh, sorry, I will just do first minus to all outputs. So this is again a what it gave us, the worst case path ending at the output is in fact starting from the input itself. Now this is why it's worst case. The output delay is 1, the input delay is 1. So you are left with 0 path class, 0 available path, right? So clock frequency is 2. Out of the total period of 2 nanoseconds, you gave 1 nanosecond on the input side, 1 nanosecond on the output side. There is nothing left for the operation you want to do inside, right? So in this case also I want to, so what we could do is, for such cases, I'll come to this later, a slide later, but for such cases we have to make sure that our input delays and output delays are not in such a way that such kind of combinational paths are constrained like this. It is a very bad constraint because it doesn't leave anything for the internal design, right? It will give all the timing away at either input side or the output side. So practical solution would be to reduce the input delay or turn off the output delay. There is one more solution, I will come to that later. So now I want to report the worst case register to register path. Let's do a report timing and see what it does. Now report timing tells us that the worst path is from start point to the endpoint register, start point input port, clock group is clock. Now for all the paths in this design, that clock group is clock. Whether it be input to output, input to register, register to register, register to output. Now what is the way to report? Simply register to register timing. What you could do, you could use a command called all register. Now, all register typically gives you a list of all registers, but it has few options called all registers minus data pins will return a collection with all the data pins of the registers, minus clock pin will return with all the clock pins of all the registers. So now I know that in case of a register to register path, the start point is the clock pin of register. So I do all registers minus clock pin, and the endpoint is any data pin. So for register to register path, the start point is always a clock. So I build up a collection of all the clock pins of all the registers. Here I have the collection of all the data pins of all the registers. Right? If I do this, it will tell me the worst case register to register path. Now this is the path. Some U7 big data raised to U7 results, right? Now let's see violation. Now in the earlier design, now what we have changed? We compare two designs: without input delays, without IO delays, and with IO delays. Now what we have changed is we have just applied input and output delays. We are just playing with input and output delay values. But do we expect a register to register bit work? No, we did not expect that, right? It is wrong. It is something. So there is some mistake we have done, so that the slack is violated in case of register to register. Ideally, input to register paths, register to output paths, you can play with the delay values. You can even make sure that your design, your ports register, make sure that functions are good and so on. But the register to register paths typically are the limiting factor for your performance, not the input to register path or output to register to output path. The IO delay, IO paths should not be timing critical. What is timing critical usually is the register to register path. Now imagine an ALU, right, of a CPU. Lot of arithmetic and logic operations go inside ALU. Typically the core of the ALU, which does arithmetic operation, would be timing critical. Right? Not the incoming ports to register or register to output. Right? Now what is the problem? Why did DC not optimize this path? We know that DC can optimize. Why? Because we have seen in the earlier example that without input output delays, without applying input output delays, DC was able to achieve a zero slack. But in this case it is not so. Why? Now the problem is that DC works on groups. Here there is only one clock group, that is clock. So DC will group all the timing paths into different groups which are determined by the clock. Now in this case, the core works on the same clock, the input delays are on the same clock, the output delays are on the same clock. DC does not have a way of knowing that whether you want to prioritize register to edge, or you want to prioritize register to input to register, or you want to prioritize register to output. So it works on all the paths together. What it does now is that, let's see report constraint again. it's a very important thing. Please make sure that you understand it, understand this concept. Now, in this case, we know that these top violators are input to register path. So it will work on all the violators, but now it sees that it cannot optimize input to register path anymore. Input to register path is optimized to the maximum, and it has so many violations. Again, register to output paths have so many violations, right? So what it does is that it spends all its time and energy into those top violating paths. If there was only one path violating, then fine, it will come to the second path. But if there are multiple paths violating at the top of the group, it will focus its energy on that. Now it knows that it cannot fix these, so it will leave out some of the rest of the paths. It will not optimize it. Why? Because every synthesis process is a time, it has some time limit, right, over it. Although it's a very small design and all that, but still. So since all the paths are in the same group, same clock group, and DC does not know any priority, it assumes that all paths are of same priority. It will optimize, and since it sees so many violations at the top level, starting from inputs or going to output, it will spend all its time and energy in solving this, and in the process, it might leave out some of the register paths. So what do we do to solve this? We do not want it to be. Now there is a much more sophisticated technique, which you should. I recommend that you use this technique always. What I'm about to tell you. Now what I do is I remove this design. Now what extra thing I do is that I use a command called group path. So what I do is that, so the first design we saw did not have any input delays, output delays. Second level of design had input output delays, and we saw that it created problems in the rest of the path. Now I'll do a group path. I issue a command called group path. I add group. I create a new group called input group, and I say that all the paths starting from input, put it into this group. Again, I tell that all the paths ending at the output port, keep it into an output group. Now I'll read in the DDC in this subject exercise. So I read in the DDC in which I have the group path command applied. I do a link, and again I do a report constraint minus all violators. Now we see that there are violations. So now it has three groups: clock, input group, and output group. The two of the groups we have created explicitly. So now it tells us per group. So max delay setup is violated in input group. It is expected, fine, because in only design also it is violated. Then these are all input group violations. Now it is very good. Now reporting part also becomes much more better. Now we know that intuitively we know that okay, input group means all these endpoints, the violation is starting from some input port, right? Then that's it. There are no violations, no setup violations in the clock group clock, or there are no violations in output group also. Now let's do a report timing. Now this report timing will report worst violators, worst case path, not only violators. If it will not be, if all the paths are not violating, all the timing is met, it will again report the path with the worst flag. So it could be negative flag or positive flag. So now the first part it reports is the path group clock from register to register. Now the path group clock in fact contains only register to register path, because we have created separate groups for input and output. So now this path is met. So we are back to good synthesis data. We saw in trial 1 that without input output delays, DP is able to meet timing. In second trial, we saw that the timing was bad. In this one, we are able to restore the timing, right? I'll tell you why. How did we achieve that by group path? Now slack is met. Now report timing will also report the path, the timing, the worst timing for input group and output group. So the second path it reports is the input group. We know that timing is violating here because it's a long path. There is a violation. Now it reports the output group. Right? Output group is also meeting. We saw that there is no violation in the report constraint and all violations. Now how did DC achieve this? DC was able to achieve this because now it sees three groups. Earlier it's only one group. So now as many groups as DC sees, it will try to meet the timing for each of those groups individually. So it tries to meet timing for clock. Now the clock has no competition with input groups, right? Clock is a group in itself, all register to register path. So it will try and meet timing, and we saw that it is able to meet timing. Now it works on input group. Now input group it finds that okay, yes, let's do a report constraint. So input group timing paths are critical now because there's a lot of combination between input and the first register. So it tries to optimize. Now it might happen that the paths lower down here can be optimized, but they are not optimized because there are number of paths that are violating more than these paths, right? So it can happen in the same group. The top violators can prevent optimization of the paths that are violating by a smaller amount. It can happen. We saw that in trial 2, right? Again, output group. So we saw that in the earlier case, in the last trial, the output group was the timing to outputs was also violating, but now it's not violating here, right? So DC will work on every group. So it's a very good practice to create separate groups for inputs and outputs, right? Either in this way or the things will change when multiple clocks will come into account, right? So the best practice is to register all inputs and outputs so that the timing constraints become very easy. Second, if you realize that your register to register timing is violating, look at other groups, and you expect the timing to pass. Look at the other groups. What the other groups are violating. Make sure that you segregate groups. So things become much more complex when you have multiple clocks. Then you have to make sure that the inputs get input delay with respect to the correct clock, not to the wrong clock. Or you could use the group path to create separate groups of your own, right? Read more about group paths. Read more about the man page in the man page. Group path has one more functionality. Group path in fact provides you with a lot of things. So let's look at group path minus. So in fact, you could also set a weight. In fact, so what you could do is you have separate groups. You have separate groups created. Now you can tell DC that this group has higher priority, so that DC will spend more time on that, more time and energy, right? By changing the weight value. If you create a group without specifying anything to the weight and the critical range, then for DC all the groups are equal, and it will meet up to the critical range of 0. But you could tell DC that I this group is more important, so please spend more time in this, so I can use this weight feature. You can read more about it and try it. Maybe in the next lab session we'll try out the weight feature, but not in this one. I just wanted to introduce the concept of path grouping and to make sure that you understand how DC optimizes in a particular group and how the top violators in one group can affect the optimization on the paths that are violating by a smaller amount, right? I hope the concept is clear. Now let's see a few other things. So we discussed about the IO delays. How does IO delay applying or not applying IO delay will affect your design. We discussed about the write command and the read back of DBC and Verilog. We have discussed about group path. Now let's see a command called change names. Now for this particular design, let me write out a, so I have written out a Verilog also. Now let's look at the Verilog. Now let's look at the Verilog. Let's look at the Verilog of no IO delays dot v. Right. Now, if you notice, there are backslash in the name of wires, and probably this wire was 16-bit wide, and it is split like this: backslash, the wire name, and slash, and N16 enter, and so on. We see that the instance names have backslashes and so on. This is the way design compiler operates when it works on a design, and we wrote out Verilog, so it will write out in the same format. But this netlist will have problems when some third-party tools will read it. Why? Because these do not follow the Verilog rules. The naming convention does not follow the Verilog rules. So what do we do to correct this? There is a command called change names. So what I did was I applied a change names on this. I said change names minus verbose, which is giving me a list of these things, and I say minus rules, and I tell DC that follow Verilog rules and change the names, correct the names. Right? If I do this, what happens? Or I will say minus hierarchy. Hierarchy is complete design. Now it is telling me that in this design, this object is a cell, and it is changing the name to this. Right? So again, see, if you see that this instance name slash is removed and the is added, so it will give you a list of all the names it changing. Right? Let's look at the net, for example. See, the net has slash in it, but here it is replaced by underscore. So you could the replacement of slash by underscore. These things are configurable. There's a command called define name rule, which you can define your own rules. But for all practical purposes, you can use name names minus rules Verilog, rule in the complete hierarchy. And now you write out the design. So the design looks like this. So let's look at the chain names design. Now the design looks like this. The instance names are corrected. There are no backslash or flashes in the wire name, and so on. So now it is safe to deliver this Verilog to a third party tool. There will not be any problem in reading it. Right? So ideally you should include chain names before writing out the Verilog. Right? So this was all about chain names. Now let's look at something called the DW module. We discussed this in the lecture that DW is short form for designware components. Designware components is a group of data path components by Synopsys itself. Let's look at the design. There is a data path component in the design. So I think it's in the path segment. Yeah. So here you could use something like this. DW02 underscore multi is a kind of a multiply module. The hash 8x8 tells that what is the, so it multiplies two vectors A and B. We are telling that okay, the first is also of 8 bits, second is also of 8 bits. You should look at the documentation before using any DW components like this. Again, this is how it is instantiated. So you could use it directly. Now second, so what now DC will do is that you do not need a Verilog for this, because this DW component, DC has the knowledge of this. So there is a design where we go back to DC shell. Let's go to DC shell again and start the synthesis from scratch. One more thing. Now let's look at the netlist. Let's look at noidolays.v and try to find if there is any DW component here. There is no DW component here in this netlist. Let's go to path segment because the DW component was here. But here we do not find anything. We do not find any DW component. There is no design by the name of DW here. Why? Because by default during the design compiler will ungroup. It will ungroup design their components. You cannot see the what is the actual architecture of designer because it's proprietary by process. You only have the information of what it does and the code information how you should, and the rest in the compile process also it will ungroup the hierarchy, and you are left with all the registers or the combination. Okay, right? How can we avoid that? Let's see. So I'll remove all the design, and now I will read in the RTL. I'll start from RTL. I'm going to show you something. I'll start from RTL. I'll set up all these things. Oh, sorry, the RTL is not there. I have to start from this one. Okay, now I'll apply the constraint. Let's not apply input output list for the thing I want to show you is does not depend on IIT list. Now let's search for a variable which controls the ungroup. So there is a variable called compile ultra ungroup DW. It is set to true. Let's set it to false. And now let's compile. It is compiling. Now in the compile log, if you save the log, it also shows that it is this is the designer building block library. It shows what version it is using. It is inbuilt. So it is using a basic and license both. So it is mapping now. Now there are two. So it is adding this designware to the list of comparators. So now there are two kinds of uses. There are two places where designware is used. Once when you instantiate it explicitly, like in the path segment we did. So it is telling me that it is implementing synthetic, means it is implementing a designer component for path segment. Synthetic library is nothing but a designer library. But when you say A plus B, then also if the designer library is loaded, DC will use one of the designer components. So it will use a DW adder. It is telling us it is implementing synthetic for adder 16. It is implementing synthetic for multiply 16 or 16. It is implementing something for counter and for comparator also. So there are a lot of designs already in designware, and DC will try and use it as and when possible. Synthesis is done. There is a command called report resources. You do a report resources minus I can see what it gives. It tells us what are the resources that this design is using. Now it told us that in path segment.v, the cell U100 was using DW02 mult, which is explicit with width 8 and it contains some operations. Right? So this is explicit, but this adder, this is not explicit. We saw only one DW component in RTL, but this one is this one chosen by DC by looking at your RTL. It saw that there was we will see the path segment what is causing this. So DW adder is instantiated by DC. This is the cell width is 16. It contains these operations, right? For each of the design, it will tell, for example, there are no multiplexes to report. Now there is one more design. It did not ungroup. In path segment, there was a DW02 underscore mult. It did not ungroup now. That is why it is showing a separate design. Now, apart from this explicit one, it used a lot of other DWs, and none of them is ungroup because the ungroup is set to false. So there is one more design. So again, see, multiply 16 cross 16. It used an unsigned multiplier, DW mult unsigned, right? And this is the implementation report. It is also telling that for this multiplier, it used this implementation. So AP parts is a type of an implementation of a multiplier. I think double P means partial product. So it is some A. I do not remember what A means. So it's a partial product based architecture. Somewhere on the lines of the boot architecture. It is area. It is optimized for area. So it shows this. Again, we will see that for multiply 8, didn't choose for multiply 8 cross 8. See, for now for multiply 8 cross 8, it also shows the same similar kind of an architecture. Now for comparator, the comparator is, we'll see comparator in detail. I have one more exercise of that. So it shows a component called DW underscore CMP. Right? So this report resources tells that resources means the DW components or adders or multipliers. It is telling us that what all resources does the compile command use. Again, for adder 8, it used something. It used a DP op. There's a DP op in design compile design component. So and so on, right? So this is the complete report. You should read this report, try to understand what it means. Read more about the report, what it does. It's not too complex. It tells what is the operation and what is the architecture it used, and so on. It also tells if it shared some of the resources. So does it have any? So yeah, it tells there's no resource sharing information. So let me see. Yeah. So there are 3 things it reports: resource sharing, implementation, and multiplexers. So it gives, for example, now let's look at one example and try to map it. Let's look at adder A. So we'll open this file adder A and see that what it does, right? This is an adder 8, so it's a very simple thing. But what is causing DC to use a designer component is this assign statement. So this assign statement A plus B plus C. Now this plus sign, these 2 plus signs will cause DC. So what the adder 8? Let me go back to. Yeah, so adder 8, it used something called DPOP. It is kind of an adder, and so this is the data path. So DPOP is nothing but a data path operator. So this data path operator, this is a cell. It contains 2 operations: add 20 and add 22. Right? It tells us that there are 3 variables because we saw there was A plus B plus C. So there are 3 primary inputs and 1 primary output. All of these are unsigned because by default they are unsigned. The width is 8 here, and the carry in is 1. The output will obviously be a 9-bit one. Expression is I1 plus I2 plus I, A plus B plus C, right? So now let's look at the. So this is the. So it tells what is the implementation. So it shows a DPOP. Now one data path operator can have multiple implementations. You can look at the design documentation to know more. But for example, a multiplier will have a lot of implementations. Some of them will be good for area, others will be good for timing. So this DPOP, now it is choosing a STR kind of a STR an implementation called str, which is optimized for area. I do not remember what str means. Let's see the netlist now. We can think what str means. Now let's look at. Let's write out the. Have I written out the netlist? No. Already. Yeah. Yeah. So I have this netlist which is designed with components. Now let's look at anything called DW. Now we see that there's in multiply 8 cross 8, or let's look at path segments. Yeah. So this is the module path segment. We see that now that there is a add 0 which is used by DC. Now it has not ungrouped it, so you can see it in the netlist. A data. So now we will compare it with the RTL. So RTL had A plus B plus C, I guess. Let's look at the RTL also. Now where is the plus sign? So this is a selector block. Multiplier is U100, and then is there any adder here? So yeah, so there's a ALU which is A data plus B data, and A data and B data are both 16 bits. So this ALU will so it uses a DW mult to calculate the product, and based on the operating code, if it's 0, the output is A plus B. If it is 1, then the output is the product, right? So to implement it, it needs one multiplier that is instantiated explicitly and one adder, right? So let's look at now. So this is the adder. So U100 was it comes from the RTL, but this one is chosen by DC. A data, B data carry in. This is a type of adder that we use. VW01 underscore add. VW02 underscore mult is our own very own RTL instantiated. So this is the way it chooses, right? So it sees a plus sign, it will find out a DW component and use based on a design constraint, right? We can look inside these modules what they contain. It won't be much of a use because again these implementations are not easy to understand. So this is the multiplier module. It's a big module. It has a lot of combination logic, adders, and so on. It's difficult to understand. It's not possible to understand from this netlist what kind of architecture it is, right? So, but rest assured that these architectures are well documented in the. Although exact code is not given in the document, but the document does tell you that if it's good for area or good for timing, or how does area compare or performance compare across these things, right? Let's look at module adder 8. So adder 8, yeah. So now I also talk about unit. So now module adder 8, I come to why it's 0 or 1. So module adder 8 contains a DPOP now, which performs the actual addition. So this module, this is the module DPOP. Let's look at this module DPOP. Now this is the one that performs addition, right? Again, this is just a combination of full adders, which was expected, right? You add 3 things, 3 bits. It needs a full adder. This is a full adder. Now the way these full adders are connected will define whether it's the number of the full adders, and the way they are connected will define whether it's area optimized or timing optimized. In this case, we saw from the report resources report that it's area optimized. So moral of the story, report resources command, use it to know what are the resources that DC will use in your design. You can use a generic multiplier statement, like you can just use a multiplication sign, or you could directly use a designer component. It's up to the application. But rest assured that for every plus minus multiply sign that DC sees, it will try and find a suitable DW implementation for you. If only if you have a DW designer license available. Right? Now let's come to the mystery of the module name of adder. Now let's look at the design hierarchy first. Now we see that there are multiple instances of adder 8. In cascade mod, there are 2 adder 8s. This is a case of unification. Now what DC does is that it by default we did not specify anything, just give a compile command, it will unify. It will make different copies of the design. So when we open this design, we check what all are the adders. Let's look at the non-design here. Now let's look at the modules here. List of modules. Adder 16. So see, the adder 16, the module name is preserved because there is only one instance of adder 16. So adder 16 is used only once. Adder 8 is the only design that is used multiple times. Comparator is also used multiple times. Comparator here and comparator here. So module adder, let me just grep. So these are the list of modules. Module adder 16, module now adder 8 has 2 modules. 8_0, 8_1. Now in the netlist that means has 2 different designs, adder 8_0, adder 8_1. Although in RTL the module name was same, but when it comes to netlist, it will make independent copies. Now when the design is synthesized, adder 8_0 has nothing to do with adder 8_1. Although the functionality is same, but the implementation might be entirely different because each of them will get optimized according to its own design goal. Right? Similarly, comparator 1 and comparator 0. Right? This what name gets used after underscore is can again be controlled by a variable in DC shell, just like the chain names can be controlled. Similarly, all these things can be controlled. You want any specific prefix to be present or specific suffix to be present, you can control that using the variable. Right? So we saw the report resources command. It's very useful to know what all resources are there. We discussed about the unification process. Now let me show you one more command which is important for synthesis. It's called set fix multiple ports net. So what this command does is that now in the logical, that RTL is logical release, right? It's not physical release. In the sense that you are only worried about the connectivity of data. You're not worried about physical release. So many times, when it gets synthesized, let's say now an input, you have assign output is equal to some input. So when it goes to synthesis, DC will not do anything special on it. It will just connect output to input, right? But when it goes to physical design, usually in physical design, many times these kind of assign statements will create issues. So always you want that there should be a buffer separating output and input, at least a buffer, and then according to design rules there will be then more buffers or buffer will be upsized or so. So also you might have a case of one register driving multiple outputs. So in that case the loading is probably increased on the register, but DC will solve it only to the extent of meeting the max capacitance on that register output. But when it goes to backend physical design, it might happen that all those outputs are not placed close together. The ports are placed far away from each other. In that case, you want a good buffer tree on the register output. So DC, what you are telling DC by this command is that you fix all such cases. So you could read more about it in the man page. So it will apply some attribute called fix multiple port net. It will insert buffers to isolate input from output ports. It will insert buffers so that no cell drives more than one output port, and so on. So this is just to make the job of the backend engineer easier. Logically, it's same. It doesn't change the functionality of the design. So ideally, before writing out the netlist, before compiling, you set this, you use this command. Again, when you compile, before writing out the netlist, make sure you use the payment command. So all these things are to make the physical implementation, the physical design to be smooth. Right? Okay. Now this command is also done. Let's look at. We saw different options in compile ultra. So we have been using no auto ungroup. We have discussed about this. You can read about most no sequential output inversion is that it inverts the sequential output in some cases where it finds that it can optimize the design better. Otherwise, what happens if this happens, sequential output, it means that let's say there is a clock, right? It drives a cone of logic. If DC finds that if I can invert this output of the clock, then my logic will be better optimized. If you don't give this, it will optimize that. It will do that, and it will invert again the input. So now the flops, many times you do not want that. When we come to formal equivalence, I'll tell you why you do not want that. So ideally, to start with, you do not want to invert the output of the sequential element. So you should always, most of the cases, you should use this. You can read about exact math, but I don't use it for that. Boundary optimization, we have discussed that it can move inverters across boundaries. Usually to start with, again, you don't want to do this, but you can do this later when you are more comfortable with the compile command. You can we'll talk about this later. I'll talk about this in the lecture slides, not in the lab. Again, I'll talk about this in the lecture slides. Incremental, we have talked about it. Again, you can split your compile into two incremental, into no design rule and only design rule. But in most of the cases, you do not need to give any of this. It's design. Then there is an option called scan. Gate clock also I'll discuss first in the lecture slides, and then I'll have a lab of it. Scan is simple. When you do scan, I've done a compile with scan. Let's see how it looks like. Let's first look at the non-scan one. No iodelays.v. Let's look at one of the flops. So this DFX have these are DFX, these are non-scan flops. It has data, clock, and queue. Let's look at the file with scan. Now here the DFFs are replaced by SDFF. So it will just replace all these blocks which are non-scan by the scannable version. So DFF is replaced by SDFF, which means scan DFF. It has extra pin called SI and SE. SE is scannable, SI is scannable. When scannable is 0, B will go to Q. When scannable is 1, SI will go to Q. Since it is just a replacement of D flip-flop by a scan flip-flop, DC, it does not stitch any scan chain, it will just convert the flop. Scan chain is not stitched. So all the scannable pins SE are tied to 0, or the scan input pins SI are tied to 0. So this is the default behavior when you give -scan. Of course, you could use any DFT tool. You can also use the DFT compiler, which is a feature of design compiler to scan. We might discuss it if the time permits. Right? So this is what scan does. So this was we have covered most of the options of compile ultra. Now let me talk about virtual clocks and how to constrain the completely combinational one. Right. Let me go to design decision, and I will remove all the design. Let's look at the RTL of a comparator. So comparator is a very simple. you cannot have a much simpler module, an RTL. It just gives, it has a 1 bit output. If A in is less than B in, it will report 1, otherwise it will report 0. Right? RTL is very simple, netlist will not be, because the comparison is between 16 bits of A in to 16 bits of B in. I believe you already know what a hardware looks like. So let's see what DC does, right? Now this is let's say you are given a task of synthesizing a component, a module such as this. It looks very simple, but now let's read it, right? Let's read this design, analyze. Or what I will do is there is only a single module. I will say read Verilog. There is a command called read Verilog, and it will do the reading, analyzing, and elaborating both. There is nothing special in comparator, so it will do comparator. So it analyzed and it elaborated also. Now what I do is, now I have to compile it. Now what is my first instant? I look at the ports. I say all ports, all inputs. These are all inputs, and look at all outputs. This is the output. There is no clock in place. How do I constrain it? Let's not constrain it. Let's just do a compile. Compile extra. Now all the options, there's no need. There's no need of auto ungroup. There's no need of no sequential output inversion. There's no need of giving no boundary optimization, because there is no hierarchy. It's just one module. So we can just give compile ultra and see what happens. So there is no timing violation. This column represents timing violation. There is nothing. Area is 90.7, so it will optimize for area, right? It will optimize for area. Design will be slow, whatever. The area is 90.7, and so on. Let's write out a Verilog. Verilog. Let's say com.v. There's no need to make a hierarchy because there's just one module. So let's now look at com.v. Now is it simple? No, it's not simple. It has a lot of comparisons, right? It has a lot of AND or OA gates, and so this is the netlist. Now I want to constrain it. Now this comparator, you know that your manager tells you or design team tells you that this comparator will sit between two flops, but those flops are not part of your design. Those flops are one is at the input side, so the A and B are coming from flops. The out is going to another flop. Now and that works at 500 megahertz. What should I do? How should I constrain it? So there are two ways of doing it. First is very simple. Now let's say you are given to synthesize this and make sure that it meets a 500 megahertz clock, and there is no clock here. What I would do is, I would assume that is a valid assumption that the flops which are lying on the either side of this comparator, there is no other combination logic to it. That means the flop is launching the data and flop is capturing the data. So out of the complete period of 2 nanoseconds, which represents the 500 megahertz flop, out of that complete 2 nanoseconds, maybe I could take 1.5 nanoseconds. Valid assumption, because it's there is no other combination logic in picture. So what I will do is, the command I would use is called set match delay. I say set match delay minus from all inputs to all outputs. This is the command I can use, and the value I can give, let's say, is 1.5. What I estimate, right? I tell DC that all the paths, I mean, if they start from any input of the design and I go to the output, each path should be not more than, each timing path should not be more than 1.5 nanoseconds. Now let's do a compile again. Is the area more? Yes. Why? Because now it is trying to optimize for time, right? Now let's look at report timing. Report timing. Now see, starts input delay 0. That doesn't matter. We have it applied. It launches in at 0, goes through all these elements and CP out, and the max delay is 1.5. So it goes from input, goes to output. Total time is 0.99. Max delay constraint was 1.5. So it tells us that it is met by 0.51. All the paths are constrained. You could actually check by using report constraint minus all volatility. Design has no volatility constraints. We are good. Your design manager is happy. You were able to do this. Now there is second way of doing this. Now you know that you already know that the clock is 500 megahertz. What I would do now is that first I would clean up the constraint. It's a very simple command to clean up the constraint. We know that report remove design remove the design, but what if I want to keep the design but remove the constraints? I say reset underscore design. It will remove all the constraints, right? The only constraint we have applied here is just the max delay. Now I create the clock. Fine. The clock is not part of my design, but I can still create it, right? By using a concept by virtual clock. I say create clock minus period 2. I create a 500 megahertz clock. I know lies outside of my design. I say create clock minus period 2 minus name. Let's say clock. It gives me a warning that it is creating a virtual clock with the name clock with no sources, which is fine. I know that. I expect that, right? Now I would say I can set input delay. Now again, let's say I want a 0.5. So again, now here I wanted a max delay of 1.5. Fine. What I would do now, I would set input delay of 0 on with respect to clock. Input delay is always with respect to some clock, with respect to clock, and on all the inputs. Then I would set an output delay of 0.5 minus clock on outputs. Now see, input delay is something you are giving to the external world. Output delay is also something you are giving to the external world. Now consider a fully combinational path. So how do you decide input output delay? The sum of input output delay should be subtracted from the period, and the time left is the one that you would be using. Let's go the other way around. I know that I need 1.5 nanoseconds for my design. I am left with 0.5 nanoseconds. So the 0.5 ns is equal to input delay plus output delay. So I chose input delay to be 0, output delay to be 0.5. You can choose the other way around. You can also choose 0.25 input delay, 0.25 output delay. Doesn't matter for combination design, for this kind of design. So the sum. So by specifying this command, let's see what happens. Again, I do a compile. So the area is very similar, probably exactly the same. And now I do a report timing. Again, you see the results are exactly same. Doesn't change. Input delay 0. What we applied. Output delay 0.5. The clock. Right. This is the way you use virtual clock to specify to constrain combination paths. Virtual clock has so many other uses as well. So first of all, why do you create virtual clock? Virtual clock is created only because you want to specify some input delay or output delay with respect to this clock, and you want to mimic the conditions that are there in the external world. Which is superior, max delay or virtual clock? There is no verdict like that. One is superior than other, but virtual clock is used very extensively in static time analysis. There are so many other uses to it. So for constraining your combination logic specifically, the combination logic might also exist as part of a bigger design. So in the complete design, we saw that there were paths directly from input to output. There were cases like that. So these are the cases where starting from input, there's a lot of combination logic directly going to the output. So you can constrain this type of design, this type of combination logic by using either max delay or by using a virtual clock. Whatever you want to use is up to you, but we will see the power of virtual clock in unit time. Virtual clocks are much more sophisticated than the max delay, and we will see that what all uses, what all powerful things we could do with virtual clock. Right? So please spend some time in reading about the max delay command, what it does. You could try out. So in this design, in this the chip level design, which I have the RTL for, it's good in the sense that it's a simple design. You could make modifications to it according to your needs. According to you should try and make this design better in terms of time. Right? Area wise, don't be concerned much. You cannot do much. It's dependent on the standard size and dependent on the kind of design you have. Design is very simple, but you should try and make modifications to it so that you can constrain it better and make sure that there are no timing errors. It can be achieved very easily, right? You just have to make sure that inputs are registered, outputs are registered. You should have some kind of timing constraint, good timing constraints for inputs and outputs. Try and simplify the design for 500 megahertz and make sure that all the paths. It would be a very good assignment to have. Right? So next lab, I would probably have 1 or 2 sessions on power, and in one of the labs I'll focus on the clock gating option of Compile Ultra and on power in general. Thank you.